Just like with alkenes, we're going to look at the acid-catalyzed hydration of alkynes, and we will see that it also follows Markovnikov's rule. So here are the two overall reactions that we're going to look at. Notice that you get a different type of product if you do the hydration with an internal versus a terminal alkyne. With the internal alkyne, you're going from an alkyne to a ketone product during the hydration. The first several steps are going to look exactly like hydrating an alkene. So you start off by deprotonating the sulfuric or toxic acid. The proton goes to one side, the other side is left as a carbocation. So you get this kind of weird looking carbocation with the positive charge on a double bond. In the second step, the water attacks, just like we saw, the carbocation, just like with the alkenes, and you end up getting the hydrated product. And then the third step is going to be that proton transfer step to yield a neutral product. This product happens to be called an enol in this case because it has an alkene as well as an alcohol functionality. But enols are not particularly stable, and especially in the presence of acid or base. And so what happens is they undergo a process called tautomerization to go from an enol form to what we call the keto form, and this is what the final product is going to look like. This actually ends up being an equilibrium process, but you can see that it heavily favors the keto form. The acid-catalyzed tautomerization process begins with a protonation of the alkene, and this is going to yield a carbocation that has a second resonance structure that places a double bond between C and O and leaves oxygen positively charged. And then water can just go in and deprotonate here to yield the keto form of the product. So that those steps are called tautomerization, going from the enol to the ketone. Again, this is an equilibrium that heavily favors the keto form, and that's because the CO bond is more stable than the CC double bond. With a terminal alkyne, the process is exactly the same as we're going to see, but you end up going from an alkyne to specifically a methyl ketone. So there's always going to be a methyl group on one side of this carbonyl, the C double bond O. Sometimes you may see HgSO4, mercuric sulfate, added to this reaction. We're not going to get into the details of that, but just don't be thrown off if you see that as an additive. Mechanistically, it begins exactly the same as the internal alkyne. You have this protonation to yield a carbocation, but notice this is following Markovnikov's rule because this time we have a clearly more substituted and less substituted side of the triple bond, and so the carbocation is going to be left on the more substituted side. And then in the second step, you get the addition of water, and finally the deprotonation to give the enol. This time, via the tautomerization process, you end up with the methyl ketone. So because you start off with a terminal alkyne there with a proton on it, you always are going to end up with a methyl group on that side of the ketone product. Let's look at a couple of examples beginning with this one. Notice that we have an equally substituted alkyne, so we're not going to have Markovnikov's rule come into play here, but we do need to think about the consequences of what would happen if this side were hydrated or if this side were hydrated. And in this particular case, you get the exact same result. You can see this scenario is different. We have an ethyl group on one side and a methyl group on the other. Again, in terms of substitution level, they're the same, so Markovnikov's rule is not going to apply, and you're going to end up getting a mixture of two different ketone products. There is no stereochemistry to consider with this hydration reaction.